Welcome. Today, we are diving into one of the biggest paradoxes in technology, which is how a massive supercomputer can actually have a worse memory than a toddler. And what's really wild is that the solution might just be hiding inside your own head, in a system that's been perfected over millions of years.
I mean, think about it. It's a strange thought, isn't it? A little kid can learn about a cat, then a dog, then a bird, and their world just gets bigger and richer. But for a lot of advanced AIs, learning a brand new task is kind of like hitting a reset button. It just wipes out what it learned a moment ago. So what on earth is going on here?
Well, the answer, surprisingly, has nothing to do with processing power. It's actually all about a fundamental conflict that every single learning system, whether it's made of neurons or silicone, has to figure out how to solve.
And here it is. It's called the stability-plasticity dilemma. See, on one hand, you absolutely need plasticity. That's the flexibility to absorb new information. But on the other hand, you need stability, the strength to hold on to what you already know. The whole challenge is that they're in a constant tug of war. If you lean too far into plasticity, you forget the past. Too much stability, and you can't learn anything new. It's a real balancing act. Now, in the world of AI, this isn't just some abstract dilemma. It's a total disaster. It has a name: catastrophic forgetting. It's where a neural network's new learning can completely, and I mean abruptly, erase its old knowledge. This is probably the single biggest hurdle to creating an AI that can learn continuously, just like we do.
So if our most powerful AIs are struggling with this, where do we even look for an answer? Well, it turns out nature cracked this code millions of years ago with a really beautiful, elegant system. Let's dig into how it works.
You see, instead of having one single do-it-all system, the brain uses a kind of divide-and-conquer strategy. It has this dynamic duo, two specialized parts that work together in perfect harmony to master that balance between learning and remembering.
Okay, first step in this duo is the hippocampus. You could think of it as a fast-moving scout. It is incredibly plastic. It just dives right into new experiences and quickly encodes all the little details, like what you ate for lunch today or the face of a person you just met. It's all about super fast, short-term learning.
Its partner is the neocortex. And if the hippocampus is a scout, the neocortex is like a vast central library. It is incredibly stable. The neocortex, you see, isn't interested in every tiny fleeting detail. It's a slow learner, and it gradually integrates information over a long time to build a really robust long-term understanding of the world, the general concept of lunch, for example, or how to recognize faces in general. So how does a fleeting moment become a memory you have for life? Well, it all starts with the hippocampus, which instantly grabs that experience. But the real magic, the part that makes it stick, that happens during rest and sleep. That new memory gets replayed over and over again, kind of like a movie clip. This allows the slow and steady neocortex to gradually weave it into your permanent knowledge base without messing up everything else you already know. It's a very patient process that can take days or even years.
But wait, there's more. Neuroscientists just recently discovered that there's an even deeper secret to this whole process, a hidden rhythm that perfectly manages the balance between learning new stuff and protecting your old memories. This all goes down during the deep, dreamless part of our sleep cycle called non-REM sleep. And it's not just a simple replay. It is a precise, two-step neurological dance, and it's designed specifically to strengthen what's important without making the whole system unstable.
The first step of this dance is something we've known about for a while. It's called sharp wave ripples, or SWRs for short. These are these intense, high-frequency bursts of activity where the brain replays a recent memory, and in doing so, strengthens the neural connections for it. You can almost think of it as hitting the save button, reinforcing what you just learned. Now, here's the catch. If the brain only did this, it would actually be a big problem. Constantly strengthening connections can make the network hyperactive and unstable. It's kind of like turning up the volume on a speaker until all you get is that awful feedback and noise. So how does the brain stop this from happening? Well, this is where a huge breakthrough discovery comes in. Scientists found a second opposing signal that follows the SWRs literally right after them. They're called BARRs, and they act as a perfect counterbalance. They quiet down the very same neurons that were just activated to stop them from getting too loud and overwhelming the whole system.
And this right here brilliantly shows the solution. SWRs are the accelerator. They're hitting the gas on plasticity to lock in new learning.
and BARs are the brakes. They ensure stability by gently tapping the brakes on those same circuits. This incredible push and pull rhythm is the brain's secret weapon for learning without forgetting. Okay, so how does this intricate brain dance help our forgetful AI? Well, this is the really cool part. Researchers are now taking these biological principles and translating them directly into code, building a totally new generation of AI inspired by the brain. So first off, they're literally mirroring the brain's two-part structure. Instead of one giant network trying to do everything, they're engineering AI with two separate modules, a hippocampus for rapidly soaking up new data, and a neocortex for carefully building that long-term knowledge. They're also mimicking that crucial accelerator and brake rhythm we just talked about. This means designing AI training methods with alternating phases. You have a strengthening phase inspired by SWRs to learn new things, and it's immediately followed by a targeted inhibiting phase inspired by BARs to lock in that knowledge without causing that catastrophic forgetting. And maybe the most fascinating part of all, they're basically giving AI a form of sleep. These new systems are being designed with offline periods where they actually stop taking in new information, and instead they replay their stored experiences, just like our brains do, to consolidate what they've learned and transfer it to their stable, long-term memory. So taking these lessons from neuroscience is creating a powerful new roadmap. And it's not just about building slightly better AI, it's about fundamentally changing how we even think about machine learning itself. And you should know, these are not just vague ideas. They are concrete, testable predictions. Scientists are now hypothesizing that AIs built with these dual-process systems will crush current models, that mimicking the SWRB rhythm will lead to much more stable learning, and that organizing knowledge like the brain does in a hierarchy will let AI generalize and transfer skills way more effectively. This quote from the researchers really just gets right to the heart of it all. The goal isn't to just build a perfect carbon copy of the brain. No, it's to understand its core principles, its incredibly elegant solutions to these fundamental problems, and then use that inspiration to engineer the next generation of truly intelligent machines. And that brings us to a really fascinating final thought. We've seen just how critical sleep and its hidden rhythms are for turning our experiences into lasting knowledge. So as we build AIs that learn more and more like we do, the real question becomes, will they also need to dream?